So hello everyone and welcome back here. So if you recall at our previous lesson here, we were able to show this particular theorem that if a point lies on the perpendicular bisector of a segment, then it's equidistant from the endpoints of that segment here. This we proved, and this is certainly a true thing here. Now, much like many of our theorems that we've been looking at so far, can we flip it around? Does the converse actually work? So do the converses of this theorem work here? So what we're going to be looking at today is, can we find the converses? Can we actually go backwards and see if this particular theorem works? So remember what the converse does here. So remember that for the converse, all we're doing is switching the situation around. So what used to be the antecedent is now the consequent. What used to be the consequent is now the antecedent. So now we're going to flip it around here. So notice how we have a point lies on a perpendicular bisector segment, then it's equidistant from the endpoints of that segment. So it shouldn't be too hard to flip it around. Now we want to start off with being equidistant from the endpoints of a segment, and then getting to the perpendicular bisector. So if you were to do the converse, it would look something like this here. The converse of our statement would be something like this here, where you can have, if a point is equidistant from the endpoints of a line segment, then it's on the perpendicular bisector of that segment here, okay? So let's go ahead and figure this out here. I want to prove this particular theorem. Now this theorem here is going to be a little bit weird, okay? So again, we're going to be given P is equidistant from the endpoints of the line. So PA is going to be congruent to PB, right? So if you think about what's going on here, we start off with that PA is congruent to PB. So I want to prove that P is on the perpendicular bisector of AB. Okay. So this particular theorem here is actually pretty difficult, because if you take a look at what's going on here in the picture, let's take a look at what's happening. I mean, we appear to have a single triangle here, and that triangle appears to be isosceles. So we can use, the isosceles triangle theorem, the fact that you have two sides of a triangle congruent, the angles opposite them are congruent here, so we can mention that. So that tells us this here. But then we seem to run out of material, right? We don't know what's going on here. So that's really strange. What are we going to do? So this is what we're going to do here, and this you're gonna have to bear with me, because this argument seems is going to be a little bit weird, right? So we know that P has to satisfy two things. There's a segment that runs through P that has to be both perpendicular and splits it up at the same time. So we're actually going to do one of two things here. I think we can agree that there exists a unique midpoint here. So let me call this point here M. I'm going to call this in green. Okay? There exists a unique midpoint M. So I'm going to draw this green line here, PM, like this. Now, it's pretty clear that M is a midpoint here based on the way I set it up. And I can do this here, right? If I can show that this line is perpendicular as well, then that works out, right? Because that means this green line is going to be the perpendicular bisector I want, and P is on it. So notice what I'm going to do is I'm going to do this here. I'm going to set it up like this here. So I'm going to let M be the midpoint of AB and draw PM. Okay? Actually, the line PM here. Now, it shouldn't be too hard to show what's going on here, right? We know that in this case, PA is congruent to PB. That's given. Right? We also know that AM is congruent to MB from the midpoint definition. And now we know we can use these angles here, or even better, we have PM is congruent to itself, so let me mention that. So PM is congruent to PM. This is reflexive. So notice that by doing this here, we actually are able to show something important. This means here that we can conclude the triangle PAM here is congruent to triangle PBM. By side, 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 right? Because I got three pairs of sides here. This is one pair, this is a second pair, and that's a third pair, PM. So thus, now how does this help us? We want to show that it's perpendicular now. All right, well, wait a minute. This means here, notice that what's going on in this situation, this green line tells us here, thus, we know triangle PMA is congruent to angle PMB. These are corresponding parts here, right? And we know that the corresponding parts are congruent, triangles are congruent. Now, because these are congruent here, so these two angles are congruent and they also lie in a straight line, they have to be right angle here. So we know that that's one of our theorems here, so that we can conclude that PM is perpendicular to AB here, right? Because these are lines that create congruent adjacent angles. One of our theorems is that if we have two lines that intersect to form congruent adjacent angles, they have to be perpendicular here. So that actually tells us something really nicely here. That actually works out really, really well. So notice in green, I can have this sort of thing here. However, some of you may know, wait a minute, that just sounds weird, because I can do something else here. So let me do this instead. All right, let me go ahead and resketch this picture. Maybe we can resketch the picture over here. Okay, here's A, here's B, and again, we're going to have point P over here. So I'm going to take the exact same picture as I did over here, but I'm going to redraw it over here. But I'm going to change it up slightly. Here we assumed M was the midpoint here, right? Now, through point M to the side AB, it's not hard to see that we can create a perpendicular, right? So let me create a perpendicular line through like this here. I'm going to call this point here N. Okay, so now I'm going to create a perpendicular like so. So notice that we have this here. So I'm going to say, let N be a point on AB, so PN is perpendicular to AB. So notice that again, we wanted to show two things true about this line. I'm actually going to pick one of them and show that the other has to be true here. So that's sort of the theme of these two different ideas here. Here, I picked the fact that it's a midpoint here, and then I showed that the other part has to work. And then here, I did the other thing around. I picked that it's perpendicular, and then I had to show it has to be a midpoint here. So we can go ahead and set that up in this situation here, right? So now, again, we can kind of do this. Argument here. We can try to show that these two triangles are congruent here. So again, we can now go ahead and use that here. So let me mention what's going on. Again, we have PA is congruent to PB. Again, that's given to us. And now we have angle A is congruent to angle B here, right? Because these are angles opposite congruent sides in a triangle, right? This is our Pons Asinorum here. This is our isosceles triangle theorem. And then we also have the fact that angle PNA is congruent to angle PNB, right? These are perpendicular lines formed. These are right angles here from perpendicular lines. So notice that we can still do exactly the same thing as we did before. We're going to use congruent triangles here. We're going to use it slightly differently, right? So in this case, we can say the triangle PAN is congruent to triangle PBN by, in this case, angle side. Right? So it's a little bit different here. You could have also used PN and hypotenuse like to prove this here. It's up to you. So we can say thus, AN is congruent to NB here, right? By corresponding parts. And yet again, we now have the fact that that tells us that PN bisects AB. Because that's we have definition here of the midpoint and segment bisector. So notice that here that we actually had two different proofs here, but they worked in the same fashion here, right? We started off, because of the fact that we didn't have enough information, we kind of had to show that one half led to the other here. There were two things I had to show. I had to show both, I had to show both P and Q here. So I had to show that P, if you started off with P, you also had Q at the same time. And if you start off with Q, you could have also gotten P at the same time. So it really doesn't matter which method you use here. Either one of these would have been perfectly fine. But notice that in this situation here, we were able to use our power of congruent triangles and a little ingenuity and show that this indeed is true. The converse does work. If you are equidistant from the endpoints of a line segment here, you have to be on the perpendicular bisector of that segment. Now, remember that this was not the only theorem that we talked about here. We also talked about one involving angles, and indeed, the converse does seem to work here, right? If the point is equidistant from the sides of an angle, then it's on the bisector of that angle. And that proof, luckily that proof is a lot easier to deal with, and you'll be dealing with that in the homework.